Hey, and welcome to the New York City F-Sharp user group. Today we have Eirik Tsarpalis, who's an amazing F-Sharp programmer. He's built tons of cool stuff like the, what's it called? The Embrace, yeah. Man, I'm so bad at remembering these things on the spot. But yeah, it's a pleasure to have him here. There's just a couple quick announcements. Firstly, like if you're at all interested in giving a talk, we're always looking for speakers. It could be like you just want to show off some F-Sharp knowledge you gained. It could be that you want to show off a cool project you did, and we can even do something where we set up like a bunch of people if you don't feel comfortable doing like a whole hour or something. So keep that in mind because we're always looking. And I think that's about it. And I'll just leave it to Eirik from here.
So thanks, Rick. Thanks for coming. Thanks for the invitation. Second time, I think. So I'm going to be talking about an idea that I have been sort of brewing for quite a few years. I'm actually using it in production, but I actually found the time during the summer to sort of polish and actually create a library out of it. It's called TypeShape, or Practical Generic Programming in FSharp. By the way, if you want to see the slides, if you're too anxious to go to the end, there's the link. You can actually type it in and see the stuff beforehand. So a few words about me. I'm a mathematician. I've been doing F#/.NET development for the past 5 years. I'm the co-author of Embrace and many related projects. And I just started working at Jet, and I'll be joining their Dublin offices, working with the backend team. So let's talk about data-type generic programming. It's an ambiguous term. Some people call it polytypic programming, some people call it generic programming. I found this quote in a paper that defines generic programs as programs that are parameterized by types or shapes of data types. And while it might be ambiguous, you might know about this paper, which was published maybe 13 years ago, and provides a way of doing generic programming in Haskell. I think I'll probably need to make a disclaimer here. I'm not claiming that I'm trying to do the same thing as scrap your boilerplate, so you're going to see something that's slightly different. But in general, there are many ways in which you can achieve generic programming. So to give you like a real example of what a generic program might look like, imagine you want to define a function called prettyprint that takes any value of any type and returns a string that gives you a nice representation, display of this value. Now, if you believe in things like parametricity and stuff like that, you would claim that this is obviously not possible, but there are ways, and people have been doing that. So let's now sort of have a look at some imaginary F# program, which you cannot actually write with the current version of F#. Imagine that I'm defining my prettyprint implementation like so, in which I actually take the value, I pattern match, and if the value is an integer, then I basically call to string. If it's a string, I just return that. If it's a tuple, I basically just introduce the two types that are part of that tuple and deconstruct and recursively call prettyprint. Same if it's an optional, and if I don't know anything else, then I call value.toString. And the assumption is that if I call my new prettyprint program with any input that matches this algebra of types, then you would expect that it will recursively sort of traverse the type shape structure and be able to produce a prettyprinted output. But of course, this is not possible in F#, and it's actually not possible in .NET, because one of the things is that in some of the pattern matches, I'm actually introducing type variables into scope, which, as you might know, it is not possible unless you resort to some kind of meta-programming tricks that aren't really compiling to real I/O. Actually, if you go inside F# core, you might see tricks like that, but you cannot do it in day-to-day code. So An interesting question here is how can you actually define this without doing meta-programming tricks? So before going there, I'll show you just a few more examples of programs that can be defined using generic programming. One would be to define a JSON serializer that takes, again, any value of any type and returns its JSON representation or failed try. And the same thing goes with the deserialization function. Again, takes an arbitrary JSON representation and tries to convert it into any type. And I suppose that this example, if you've played with fscheck, is also pretty familiar. The arg.generate function that you use to basically, generate arbitrary values for any given type, assuming certain requirements that it is an algebraic data type, etc., F-sharp record union. It will actually going to be generating legit values for this. But how does it do that? I mean, how do you define libraries that implement such generic programs? And the reality is, going back to our pretty print implementation, is that you actually need to use some reflection, at least some. And I'm going for the maximal approach here. So my pretty print function, if it were defined using standard reflection, it would look like this monstrosity, which, as you can see, it's really long, it's really hard to read, it's very easy to make bugs. If certain properties change names, then the compiler will not be detecting those changes, and you get runtime errors, and it's an overall mess. I mean, everybody who's ever worked with reflection knows this. This is not nice. This is not pretty. So I guess the question is here, how can you actually avoid doing that? Or at least mostly avoid doing that? So yeah, reflection, tedious, unsafe, ugly, slow.
But how do you feel, really?
So let's go into some functional design patterns. So how many of you have heard about the visitor pattern?
Is this not OO? This is not functional.
Yeah, well, it depends on your point of view, I guess. Okay, quick review of what the visitor pattern is. Assuming that we are working with DLR expression trees, some of you might have done that. The expression type, which is actually an abstract class, defines a method called accept, which takes an entity that's called expression visitor. And what this expression visitor is that it basically defines a bunch of methods that can visit different instant types of a specific expression tree node. So what the visitor pattern essentially is, it is a design pattern that lets you sort of traverse expression trees, essentially. I mean, most of you know this, so it doesn't make much sense me trying to explain this, but I think that it's a common, a common belief in the F-sharp community says that in F-sharp, if you resort to using DUs and pattern matching, you have no need for visitors. And this is like a correct assertion. I mean, pattern matching is so much more powerful than having to write all those crazy visitors. So I'm going to reference this publication done a few years ago by a couple of people at Microsoft Research, which basically proposes implementing GADTs in C# by basically using visitors and also introducing a slight modification to the type system, namely type equality constraints. I mean, it's not the purpose of this talk to present the contents of this paper, but to give you a sort of rough idea, we take the previous expression visitor and we sort of make it a bit more general in the sense that this is actually a generic type that takes a type parameter R, and each of the branches actually return R, and each of the constructors, or rather abstract methods, might actually in certain cases introduce type variables because they're generic methods. So if I were to define a small expression-like language in which basically defines a simple lambda calculus, you can see here that my apply visitor actually deconstructs into two expressions of whom the type is introduced by the type parameter of the generic method. If this doesn't make any sense, I could repeat it. But the basic idea is that if you've ever seen GADTs in Haskell, you can sort of squint and turn your head and look at the iExpression visitor and kind of see that it kind of looks like a GADT definition, but it's not quite the same thing though. I mean, it's largely different, sort of the same. And the fact that it's not exactly the same means that you also have to define all this boilerplate code in which you define all those special cases of our expressions. So for example, if we sort of focus on this apply expression, it basically exposes two type parameters. It takes a left expression, which is a function type, and a right expression, which is of type value, and we can then accept our visitor by applying the left and right with the type variables. So going on, I can actually define some stuff that actually construct expressions, and in this case, I have a constant, I have an add function, if then else, and an application which basically looks like a constructor of a GADT because it actually takes something that has a type variable b, and then it becomes a is actually removed from the type of the underlying expression. So what you get by doing all this is that you can actually do something that kind of looks like pattern matching, but is really very ugly, mostly because it includes all this unboxing stuff. And this is actually because the type system in F# and rather .NET is not smart enough to sort of deduce that actually this type A is not equal to type T. So I have to actually perform a runtime conversion at risk of this actually blowing up at runtime, which I sort of know that it doesn't. So I guess this actually applies to the original paper, which also introduces equality constraints to the type system, and this would make the problem go away essentially. But it's still something that kind of looks like GADTs, but not quite. And what you get by this is you actually have strongly typed expression trees, of which if you sort of actually try to change the value of something, you get a type error. And to see if I can actually demonstrate this, I have actually exactly the same code copied over here. So I have this guy, which is, let me try to assign this. So this is an expression of type int. This is an expression of type int. If I actually try to put a string here, it'll actually complain because expressions use strong typing here.
Can you increase the font size?
Yeah, sorry. Oh.
Yeah, that's going to.
Yeah. Sorry, it's a new computer. I'm still learning the keyboard. But this is besides the point. I was basically just trying to, I guess, introduce the benefits of, maybe try to convince you that the visitor pattern has a few merits, which cannot be achieved through standard pattern matching. Let's now investigate how this can actually be used in generic programming. So I guess the observation here is that visitors with polymorphic methods kind of look like GADTs, but not quite. So let's try to take this observation now and apply it, take it to a logical extreme, and sort of say, what if I actually define a type visitor that does not actually visit any values? It only visits specific types. So to take a really simplified form of this implementation, I define this iType visitor interface, which again returns a value of type R, and you actually visit, and the only input here is basically a type parameter, nothing else. So what can you do with this kind of thing? And essentially, what would be the entity that accepts this kind of visitor? And in this case, I'm defining something that I call TypeShape. doesn't really matter. I mean, the reason why I named this is historical, really. I don't think it actually applies to anything right now, but it kind of stuck. So implementing this TypeShape gadget, you actually define a strongly typed version, which is generic, and then we accept a visitor by passing the generic parameter of this specific object instance. So another cool thing is that you can actually use reflection to instantiate instances of TypeShape without actually knowing the type parameter at compile time. So I can actually take any system.type, do some reflection magic, i.e. applying T into our TypeShape, and then use the standard reflection methodology of instantiating this guy, which you can actually do. And to give you an example of how this can actually be used, let's consider this little snippet. Here I'm actually getting a type which obviously is not understood at runtime. I'm creating a type shape of this, and then using FSharp's object expression mechanism, I'm actually defining inline a new visitor, which basically when invoked will be passed system int32 as a type parameter. And if you actually try to run this, you'll be getting this example, this result. So what does this mean? What it really means is that this technique actually lets you introduce any system.type instance as a type variable inside the scope of the visitor. So when I gave you the first slide, let me just scroll back, I mentioned that this is fake F# because in this line I'm actually introducing two type variables into scope that didn't exist in the method body. So how could this be done? And going back, my claim is that it could be done like this. So I mean, how is this even useful? So let's have a look at an example that is, you people might have seen this. Suppose you have a static method that is generic and I guess takes an optional value of type T and returns something. And the goal here is, suppose that we do not know what the type parameter is at compile time, and we would like to implement an untyped version of this function that basically takes any value of type object and then calls the above my method implementation using as type argument the underlying system.type of that specific object. And you know, if you've been writing like libraries that do this kind of stuff, you might have seen this piece of code that actually uses reflection to achieve this. So there are quite a few steps going on here. First, I take the underlying system.type of the object, assuming, of course, that it's not null. Then I'm using a bit of reflection to actually find my method and then make it generic to my specific type. Then, of course, we need to remember that the argument is actually optional. So when you pass the method, it has to be, it shouldn't be T, it should be T option. So there's more reflection ugliness going on here where I'm actually wrapping my value in an optional type. And once I've actually done this, I can finally invoke my method info with that optional parameter and expect a result to appear. So, I mean, you might have seen this, and I mean, I'm pretty certain that your code uses code, relies on libraries that do this kind of stuff. And it's really ugly, it's really unsafe, and it's really error-prone, especially when it comes to refactorings. Because if I were to either rename my method name or add an additional argument, this would automatically fail, because it would not, any change would not be caught by the compiler because it uses reflection. So doing the same thing using this TypeShape abstraction that I showed previously, you can actually reduce it to this definition, where again, you get the underlying system.type of the value, you get back the shape instance, and then you can actually use that to pass a visitor, which will introduce the underlying type of the object into scope, and then I can just call the generic function, and this works. Of course, it comes with certain unsafe aspects. So the unsafe aspect here is that I'm downcasting into T, but I mean, the compiler cannot guarantee that this will succeed. I sort of know that it will succeed, but again, it's not completely type safe. But in any case, it's definitely much better than this approach. The thing is that if I change anything in my method, then it will automatically be caught by the compiler at this point. So if I change anything, it will complain. I'll be getting squigglies at compile time. So I believe this is legitimately useful. A bit ugly, I guess, but again, it's useful. So let's now see how we can actually use this pattern that I showed you and apply it into more complex type shapes. So to give you an example, assume we have a pair, a tuple of two parameters. Again, I can take this iType visitor and expand it so that it takes two type arguments, which in this case are the two components of our tuple. Again, I can define my untyped shape tuple, which accepts the visitor, and then I can implement this by, again, creating a shape that takes two type arguments and applies and accepts the visitor by applying the two type arguments to the method body. And then again, if I don't know the tuple type at compile time, again, I can use a minimal amount of reflection to actually instantiate my shape, and then I can use this to actually introduce the two type variables into scope. If you can see here, I'm actually defining this as an active pattern with holes, because it might be the case that my system.type is not a tuple. So this can be very useful. Other shapes could be, defining a shape for an F-sharp set, which carries the additional constraint that the type variable should satisfy the comparison constraint as set by the F-sharp compiler. Again, we can introduce this into scope by designing our own iSet visitor that brings this inside. And again, I can define my active pattern that takes a type, does a minimal amount of reflection to deduce the type arguments and whether it's actually an F-sharp set, and it will construct my shape set. So there's a pattern going on here. So, without further ado, I'll show you the actual library and some cool things that you can do with it. And also the code, again, if you want to have a look. It's available on GitHub on this website. So, just evaluate those things. I guess many of you might have seen this implementation, activator create instance, which under the hood uses reflection. It basically uses the reflection library to find the constructor that has no parameters, then invokes it, and gives you back the instance that has been created by this reflection-based invocation. Okay, so assume I wanted to define a variation of this, and actually I've picked up the need for this implementation from an actual library, FSharp Azure Storage in FS projects, where Daniel, the guy who's the author of the library, goes as far to actually use the FSharp quotations evaluator to have a fast way of instantiating values without resorting to reflection. So let's see how we can do the same thing. In our case, using TypeShape and no metaprogramming. So let me just, of course, the first thing that I'll do is I'm going to create a shape instance out of our type variable. Then, well, I'm just going to start the pattern matching in any case. So I'll just put this here. And then Basically, the library comes with assuming that IntelliSense decides to work, I guess. Okay. I think I might actually need to remove the annotation. I don't know why it's not working. That's interesting. Sorry, I have IntelliSense dying on me at the moment. Okay. I think I might restart Visual Studio. See what happens. That's very interesting. I don't have IntelliSense. Anybody know why?
I think sometimes it wanders off to go parsing things, but it wouldn't be that.
Close the other guy. I mean, it's not working at all. I mean,
What if you commented out everything prior that you did? Like that in the main submission. Does the X, no, it's fine.
okay, I'll comment out everything. That should work. Ah! But I still need this guy. So. Okay.
Bring in the TypeShape.
You're erasing guys here.
Thank you. I don't know what happened there, but okay. So it's really strange. This is actually the first time that this has ever happened to me. I don't know why. So might be this guy. Okay, I think I might. Hey.
It doesn't like the shape. What happens if you bind TypeShape create to a variable?
Sorry?
If you bind TypeShape
Yeah, I'll try
create
that.
to a variable?
I've never seen this before. Like, this is a problem. Throw it in the window. Yes.
Wow.
The shape for solve on 7?
At Karma today.
I have no idea what's going on. It's probably too obvious.
That's drunk BS.
That's drunk BS, yeah. I don't know. So I guess if I just it's working now. It's for some reason it complains when excuse me. Yeah, at least it's complaining now. No, it's not gonna work today, sorry. I might just jump to the next sample, which might also not work. I don't know. Guess the terms of live coding. But again, this is a variation of the slide that I showed previously, which is basically again invoking a generic method in a generic class. Again, the goal here is to implement invoke and type, which takes the two parameters t and s as boxed arguments, and then properly invokes the generic method using right type arguments. So again, I have implemented this monstrosity that uses reflection. I'm just going to just verify that it works. And it correctly wrapped my arguments into the FsHarp optionals and invoked the method. So the thing is, and I hope this actually works now, how we can do the same thing with TypeShape. So this is about 20 to 25 lines of code. I'll do the same with TypeShape, and hopefully this works. Again, this is assuming that my inputs are not null, which I guess for the purposes of this demo is good enough. So, I have this nested ugliness. And then, oops. Oh, sorry. Let's find the method. So this is it. So I'm basically introducing type variable t into scope, then introducing type variable s into scope. And if I try to actually invoke it, I guess, again, it'll invoke the generic method. I'm not claiming that this is more beautiful than the other. it's obviously ugly, but for taking pragmatic considerations, it actually solves many problems. But in the beginning of my presentation, I actually promised to speak about generic programming, and this is not even close to that. So for the final part of this demonstration, I'm going to try and implement using, again, live coding, so my issues, the printer that I defined previously. So I'm saying here, implement a pretty printer that supports the following algebra types. It's a mouthful. But in any case, I would like to sort of support nice printing for all the types that are described here. So basically anything that is a tuple or an optional or a nested optional or any combination of these generic types. So let me just go ahead and try to do this right now. And I have my implementation waiting. So this is basically a function that takes a type parameter t and returns our pretty printer. Oops, that's a wrong type actually. So that's more like it. And returns a pretty printing lambda that we are ready to use. So let me just go ahead and do that. I'm hoping that this will actually work now. I mean,
Can you paste it or something?
it works here. I don't know why.
Can you put quotes around it and then take the quotes off and maybe it'll already be up below?
I'll try this. Let's see if I'll use the untyped version and just to be safe.
What if you put quotes up and then you're in a quote, then it's not trying to interpret it?
Do what?
Quote shape. Just put a quote before the word shape, and then it won't try and.
Oh.
No, below. Just down below. Just
this guy.
Just make it a string while you're typing it, and then take the quotes off as a surprise.
Like this, you mean?
Yeah, and then just you won't get IntelliSense, but you may be able to actually type.
I'm not sure what you.
Well, I mean, you're not going to get IntelliSense, but you'll be able to type because you can't type a word. You can't type anything there, right? Or is it just IntelliSense? Oh, sorry, I thought you were jammed.
I don't remember my API, so.
Yeah. Sorry, I thought it was just jammed.
No, I'm basically trying to get the code completion.
Oh, how about this? I
mean, it works now.
There you go. So copy paste, and then throw the laptop at someone when you see him tomorrow.
Okay, so I'll do that. You need to combine this with the fact that this is a new laptop and I can't type on this keyboard still.
Was it missing?
Might have worked, but okay. So what I'm doing here is I'm actually creating a pattern match, which actually relies on active patterns to deduce the actual shape of the type that we are using. So if we are in this clause, we know that the type parameter t is actually an integer. So I can actually go ahead and define my pretty printing lambda just by defining to string. Of course, this will obviously complain because the type variable t has been constrained to be type int. Of course, the type checker doesn't know that uppercase t is the same thing as int in this context. So for this reason, I'm going to create a wrap function, which will basically attempt to reconcile at runtime the two types. So the way that I actually do this is I take any pretty type, and then I invoke to t string. If I put this here, then it'll stop complaining. Of course, this is not safe, but it's the only way you can actually do this. And you are sort of hoping that this conversion is going to succeed at runtime. The same thing happens. No. I mean, it's not displaying IntelliSense, but it's not complaining. I mean, it's actually been able to find the thing, so it's like a blatant Visual FSharp bug happening before your eyes. So
Somebody called Don.
So again, since this is a string, what I do here, I would basically want to I'll just carry this. Does that work right? If the shape is, let's see what else is a Boolean, again, you have to annotate this stuff. Just rely on sprintf for the moment. Okay.
Oh, I'm missing an F.
So if it's a character, again, is that correct? Might be, I don't know.
Looks like
Yes. So I guess this settles the primitives. I mean, the primitives that I've been requiring. Oh, let me also add unit, shape unit. Okay. So let's try doing something a bit more interesting and something that you couldn't do already, right? So let me try to cover the case of F# optionals. And let's see, did I type this right? It's crazy. I think it's right. So the thing with the F# option active recognizer is that it actually returns a value of type I-shape F# option, which is basically a different shape instance that can accept optional active recognizers. Optional visitors. And the way that I can actually take advantage of this is that I immediately call s.accept, and this will take an I-F# option visitor. It's all very functional, doesn't it? Of type, well, string, and then I define a visit function which I'm introducing a lowercase t, which in this case is actually the value contained in my F# optional, so I can actually use that first and foremost to be able to deduce the pretty printer for the nested value. So just going to make a recursive call to make printer with lowercase t. And so this is something from t to string. And then I can actually, so this is actually pre-computing the value, and now I can actually define my lambda, which basically takes, if it's none, then print none. If it's some t, then do some. So this basically takes the element of our optional and prints it. I think it's worth noting that this recursive function does not do the actual pretty printing. It's actually just generating printers. You might note in the end that this comes with quite a few performance benefits because the actual cost of reflection that is hidden behind the active patterns is only being forced on you at generation time, not at actual printing time. So moving on, we try shape FSharp list of S, which again returns something different. Let's check this out. I shape FSharp list, which again has another accept method. Basically, all of those instances basically have only one accept method that accepts only one visitor that has only one visit method. So you're pretty flexible in terms of the hierarchies you want to define for the algebra. So again, I can define accept method. This takes an IF_sharp. Rick, is this the first time you're seeing visitors in the FSharp NYC?
It may be, yeah. So writing FSharp for a long time.
Yeah. So I'm looking forward to this. Sorry. So again, team string. Oops. Again, I introduce a lowercase t, which is the element type of my list. I pre-compute the element printer, and then I can basically just grab the function. In this case, I'll be taking yes, the list, which shall be, let's see now. So seek map. Yes, string cut. Oops. That's incorrect. So I'm mapping each of the elements of my list to my element printer, and then I concatenate by separating by a semicolon, and then I put everything inside brackets. Again, you can see a pattern here. I mean, you can do the same thing with array. I'm not going to go into that. Let me try FSharp set, just for the fun of it. Oh, it's actually working now. I don't know. FSharp works in mysterious ways. So, again, I FSharp set visitor string with. So now I have a lowercase t, but because we're talking about sets, I need to actually introduce a constraint here. So, I'm just going to do that. So now I have the type variable inside my scope. I can actually, again, implement my element printer, do my wrapping stuff. Let's see now. And now notice that this actually works because T satisfies the constraints required by the type argument, so this basically just type checks. And again, I seek.map, element printer, string concat, and for arbitrary reasons, I'm going to do the same as list, but I'm just going to prefix it with a set keyword. That work?
Why the brackets?
Oh, I don't know. Basically, just to differentiate it from a list, I guess. I don't know. Something else. It doesn't matter. It's just arbitrary stuff like this. Okay, so for the sake of completeness, oh, now it's not working anymore.
Ow.
Okay, so it's probably in every other branch that it actually works.
Oh.
Anyway, just going to go with tuple 2.
Maybe Don put a visitor pattern detector in there. Like, no.
Well, it did work in the morning, so I don't know.
Maybe it doesn't work until you put like at least one character in there. Because it's working now.
Yeah, I had to actually add this guy to actually get it to work. So this is basically, again, an active recognizer for a two tuple. Again, you can do this with 6 tuples, etc. So it goes up to 8 in .NET. So depending on the amount of coverage you're willing to do, you can basically make this a really enormous pattern match. So let's stick with 2 tuples at the moment. Again, accept. Oh, that's what it's showing. Tuple 2 is here. String. And notice that this is because of restrictions in F# object expressions. I have to explicitly put all my type arguments into brackets. It cannot be inferred, so it's a bit of an annoyance, I guess. Again, we have a lowercase t1, lowercase t2, and these essentially denote the 2 elements of my tuple. Again, then I do my wrapping magic again. So and well, one, 2. So excluding the wrapping magic that I do, everything else is safe. So chances are that if you're careful enough, your code is going to be correct, and certainly much better than using reflection. So I think for a final thing, I mean, there are many shapes, which, okay. Let me just go through them here where it actually works, or used to work.
Take the bottom line.
Hmm?
You got the bottom line.
Yeah.
They'll probably work.
You think that was the reason? Maybe I should just add this.
Maybe.
Okay, I'll try that. Okay, so I'm just going to give you an overview. You can actually read those. It says array, 2D, 3D, 4D, Boolean, byte, byte array, character, collection, datetime. Well, these are primitives, obviously. Shape enum, which is interesting because it comes with its own interesting set of type constraints that you need to satisfy. Same with nullable, F# choice, functions, lists, maps, options, records, unions, GUI, hash set, key value pair, nullable, resize array, timespan, tuple, like lots of stuff in there. So I'm just going to implement a F# record 1, which I think might be of interest. So I mean, in .NET you have nominal typing and all, so you cannot really use, construct records and unions only based on the structured types. You actually need to do at least a bit of reflection. So there's no one correct way to do this. I actually added this active pattern as a proof of concept, though I think it can be improved. And by the modular nature of the library, it can be augmented by other people. So let me just show you how it works. Again, it has the accept method, of course, but it also carries a bit of additional metadata, like the constructor info of the record and the set of property infos that the record carries. But let me just go with accept. And again, it's like the same ritual, i.e. shape F# record 1. Again, my return type is string.
Oh, it's not a visitor?
Oh, yeah, that's right.
Eirik.
Shape. That's the one. Okay, so this is an interesting thing. So this introduces a bunch of type variables. I actually need to see the type definition because it won't infer it and I can't remember it. So it's this guy, I shape. I actually have to typo this because it's the, I guess it could be improved, but that's how object expressions work. Yes. Again, this is actually a visitor that does accept a parameter, and this is actually a type version of my FSharp record that carries a couple of methods, including project1, which takes a record and returns the first field, and it also takes construct, which takes one field and returns the record type. So it's basically projections and constructors. This basically uses reflection under the hood, obviously. I mean, since you don't know the type a priori, unlike generic types, you have to rely on reflection. So if I were to define a pretty printer for this case, I would again have to compute the pretty printer for my field, and then I would take my record value and basically just sprintf. Is that right? I think that's right. Then I would see. We also get. This is actually a part where I am using a bit of reflection. Field name and printer. Project1, which takes the record, applies the projection, and then pretty prints, and that should be it. And of course, I mean, you have to live with the fact in such programs that use reflection that certain types are not supported. You have to live with that ugly truth. Supported type. Or, I mean, I could just do this. I guess. Basically just rely to the toString mechanism. Might be a bit cheating, but actually, I don't even need to grab this. So that's basically it. Okay, so you're actually seeing this error now. This is because one of the restrictions in the CLR, because when you define recursive functions, you can't actually call to yourself with a different type parameter, but there's a really easy workaround, and it's basically this.
Yeah.
Basically, replicate the whole thing, and well. And still complaining. It's interesting. You know, obviously we're in the twilight zone of the .NET type system at the moment, so crazy stuff like this can happen. Is the air conditioning on?
It should be on. They
I
said
think
they
we're
turned
better
it on.
off with the windows, I think.
I know. I was worried like I won't get any recording though, because it'll be like
Yeah,
loud.
a bit too noisy. Okay. I'm not sure what's wrong here. I might as well skip to the ready solution, which has everything, and it works. So I obviously just screwed something up in the previous thing, and this has many more types. Actually, it has 2 tuples, it has 3 tuples, it has lists, arrays, sets, records, all this kind of crap. Let me show you how this version works, and quickly discard the live coded one. So there you have it. I have defined my print printer, which works for some types at least. And you know, not that I'm showing off or anything, but you know, the fact that you actually do not do any reflection at printing time, only at generation time, makes it quite fast. And actually, benchmarks are usually lies, but just going to show one in front of you. So I have this test type, which is basically a type shape that sort of conforms to the algebra that I've defined in the previous implementation. And I have a value of this type, which contains some random data inside. And then I'm going to benchmark 2 implementations. One is sprintf%a, which is found in F# core, and the other is basically the pretty printer that I just generated. Let me just show you how each of those things look. So by virtue of the fact that this relies on reflection, you might be getting this type of output. So it cannot really differentiate between nulls and nones, and units and nulls, so you don't really see this. If you actually use this version, you actually get this differentiation because it actually carries contextual information of the type. So
3 times faster.
So spoilers ahead. Just run this, just to convince you that I've not fabricated the numbers. So this is the first one, which uses sprintf, and this is the second one that uses the generated printer, and it's significantly faster because the actual generated thing basically is just virtual poles. There's no reflection involved. It's basically a generic program in, I guess, the full sense of it. There you have it.
So given that you know, if you have the record type ahead of time and you're doing the reflection, shouldn't there be a way to be able to like support any number of members and just omit the code?
Yeah. You could actually do that. So I'm actually using this now. FsPickler basically depends on this library for the composition of automatic composition of picklers. But for arbitrary records or arbitrary classes or arbitrary structs, in the end, I have to do some reflection emit because the library is not good at handling, I guess I would call it, records of arbitrarities. You have to sort of define record 1, record 2, record 3, up to whatever number you actually care to define. But if you want to support arbitrarities, then you have to get your hands dirty, and at least for the general record case, either use a bit of reflection or reflection emit. But there are also a few other tricks that I want to experiment with, but we'll see how that works out. Again, you know, in the twilight zone of the .NET type system. Maybe I could show you a few other examples. this is basically a generic program that for any type T generates an empty value of it in a structural way. So it creates records that contain empty strings, 0 values for the values, blah blah blah. I'll just run it. I mean, it's better to show than to describe like this. No. I'm finding bugs.
You missed the top line.
Yeah. So again, I have this guy, which is just a record that has stuff in it, and I basically just want to create an empty value. And the way that I do is I basically just call my empty generic program, and it fills it out with stuff. So empty GUIDs, empty strings, and it's really useful with I guess update expressions and lenses and this kind of crap. That's one example. Let me show you a few others. Equality comparers. Again, equality comparison using generic programming. Gmap. This actually I picked up from Scrap Your Boilerplate, where you can actually sort of query on type shapes. I won't go into too much detail. I like this one. This is a parser, which is like the opposite of the pretty printer. In this case, I'm using fparsec, and actually in the generic program here, I'm actually returning parser of t values, which are fparsec expression, I would say, like combined expression values. And the thing is that in this case, you basically just compose fparsec building blocks, and when you eventually get to run it, it's really fast because there's everything has been composed in a type way, and it's just working. So I mean, this is a really potent combination of fparsec and this library.
So you don't have to do all the backtracks and all that.
No. So yeah, again, wrapper magic. Obviously, if the .NET type system were to support equality constraints as the paper proposes, you wouldn't have to go through this ordeal. But I think that the benefits far outweigh the drawbacks of allowing this kind of stuff in your code. Let's see what else. So pretty printer, and then of course FsPickler does. I guess I want to show you the actual code. So if you go to the project, you can probably see the biggest implementation here, which basically matches against most types that we're actually supporting. In the cases where tuples, dictionary list optionals, so essentially it takes the idea of pickler combinators and auto composes them using generic programming.
Was Pickler slower before you did this?
Actually no, but no, actually it was, to be honest, because I didn't have a good way. So the idea came about in a much more primitive form when I actually wanted to compose picklers without boxing intermediate values. And this basically came as a natural way to sort of compose pickler combinators without going through this. But again, I mean, I have this struct field pickler, which does magic, basically. So it reads the fields and emits code that actually defines the serialization. So I don't, like I said, I don't have a solution for the cases where you have like arbitrary nominal types. You still need to do stuff on your own there.
So that's
at the time that you run the pickler to access reflect?
Sorry?
So when you're actually
Generating.
when you're pickling your class, does it do the reflection when you're pickling the class or before when you pickle the class?
Before.
Okay,
So
it's
it
still
has
done
a,
beforehand.
it has a generation time,
Right.
Which is again runtime,
Right.
Where it does all the composition, it does reflection, of course. I mean, each of those active patterns do hide an amount of reflection, but as soon as a pickler of a specific type is generated, it will be stored in a cache and be reused upon request. So it's basically memoizing this thing.
Mm-hmm.
You might have noticed that TypeShape is essentially one file. It's albeit a big file. It's about 1,000 lines of code. But the idea is that since it's a library for library authors, you might not want to have it as an external dependency. So you can, of course, use Packet and introduce it in your project, and it's ready to use basically. And also by default, everything is internalized, so it's not even being exposed in public API. So future work, I mean, it's mostly stuff that we've discussed, I guess, and they lie around the same theme. How do you actually support arbitrary classes? How do you support arbitrary structs? How do you support all this kind of stuff? I mean, smart people like Anton Tajanovsky, I think, might come with good ideas of dealing with this, but so far you basically need to get your hands dirty and do a bit of reflection at least. But I think in many cases it's very useful, and I'm actually surprised by the versatility of this thing. I mean, I'm actually using it, as I showed you in the previous examples, in cases where you don't really have generic programming. You basically just want to get a default constructor. Let's see if I can retry this previous example, because I kind of like it. How do you know what's at fault? So again, this is the activator thing. Hey. So I have this default constructor thing that again takes a shape, and then this accepts default constructor visitor big names, which returns what's the, don't remember the constraint exactly, but you basically do.
I think it's just NIT, or is it called this?
Something like that, I think. Okay. So yeah, that needs to be, oops. That's a different type, so I'll make it lowercase. So basically what I'm doing here is I will just return lambda equals ut and I need to close my object expression, and that's it, I guess. We could test it. Does anybody remember out of his head a type that has a parameterless constructor? Let me make one. Yeah, that works. So if I try option, it will return none because it doesn't have a parameterless constructor. If I do foo, will give me something. So if I will give me an instance of type full option. So if for whatever reason I did not have access, if I did not have access at compiling time to the full thing, I would not have to worry about the constraint. I just pass it to TypeShape and delegate the introduction of the constructor constraint to the visitor pattern. I have some other crazy stuff, like if you're into polymorphic recursion, you can do some nice things, like for example, define a function that takes a value and takes a number, and then returns you nested optionals up to that number. So that's fun, but maybe another time. So going back to my slides, I think I'm done actually. That's it.